Hello everyone, welcome back. So today we are continuing our tree series and now we will delve into each one that we saw in last video. And today we are going to cover binary tree and binary search trees and subtopics of definition, application and types we are going to cover in today's video for these two. So first of all, let's see what is a binary tree. We have to first see what is the definition of a binary tree. So we can say that a binary tree, I'm just writing BT, is a hierarchical. So the tree is a hierarchical data structure. So binary tree will automatically be the hierarchical data structure with at most two children. Now the most important words in this definition is at most, which means at max. There can be 0, there can be 1 also. If I draw a tree like this is a binary tree. This is a binary tree. This is also a binary tree. But if I do something like this, now this is not a binary tree. Got it? So that's the definition says for binary tree. Let me remove this. So I think we are done with the definition. Second point we can say is what are the uses or applications. I think we covered this in previous lecture also, but in this one we are delving more into depth. So one of the most common application of a binary tree is in representing arithmetic expressions. In the video for stack, we saw how a stack can be used to solve the expressions. But here we are representing it. So for example, you want to represent something like 5 plus 4 into 3 minus 2. I have not put any parenthesis, but we have to follow the BODMAS rule. Okay, so our algorithm says that all leaves will be operands and inner nodes will be operators. So when you have to represent this, make sure that BODMAS rule comes. So you have to first evaluate those. So our algorithm says 2 steps that all the leaves should be operands. So 4 and 3 should be evaluated first. And the operator will be a multiply. Next says its result will be subtracted from 2 and its result will be added to 5. Now when you traverse this or you want to solve this expression, what you will do is you will start from the root. If you get an operand, use it. I will write 5. Then plus. What is next? An operator. So that has to be solved. Now this is an expression. So let's say that this entire thing will give me something called T1, temporary. So T1. We can remove this. Now when you go further, you can say that when I got T1, how should I solve T1? I will solve it like this entire expression I can say as T2. So I will say This is our answer, complete answer. Now we can say that T1 equals T2 minus 2, and then T2 will be 4 into 3. Can you see this? And now when you put all these things into the main expression, if you replace in T1 its value. So what I will do is, I will replace T1 with T2 minus 2. More specifically, if I'm going to write this more clearly, T2 here, T2 minus 2. And if I again say what is T2 in a further bracket like this. So our tree hierarchy is determining the order of evaluation. So this is very, very common usage of a binary tree. Another usage we can say that is in our routing algorithms. Because we have to take a decision where we have to go and like those. Okay. Third point we are going to cover, what are different types of binary trees. First one is a full binary tree. It means every node has either 0 or 2 children. So if I draw a tree, this is a full binary tree because the nodes are either having 1 or 2 children. Second point is complete binary tree. This one we covered in the introduction also. It says all levels are filled except last, which is filled from left to right. So if you see, the current example is a complete binary tree as well. It is still a complete binary tree, but now it is not a full binary tree because I have added a node which is a single child of one of the node. Now this is a full binary tree. Even this is a full binary tree, but this is not a complete binary tree because one level is partially filled and next level is filled. Now this is not a complete binary tree. Okay, this is the difference between the two. Now the next one, the third one, is a perfect binary tree. This one is a perfect binary tree. So a perfect binary tree will always be a complete and a full binary tree. It says all nodes have 2 children and all leaves are at same level. And the fourth one is called skewed binary tree, in which only one node is filled at each level. So if you want to make this a skewed binary tree, then what you have to do is you have to remove this part and remove any of the part. Now it is a skewed one. Only one node is filled at each level. And this is the worst case. You can say that this is the worst case. I mean, this is something like you do not need a tree. It's you can represent better this in an array if you have something data that is fitting into this form. Right? So we should always avoid having a skewed binary tree because it's not solving any purpose of a binary tree. We are not making any decision. We are just traversing in a linear fashion. So that's all about binary trees. Next, we are going to cover binary search trees, most widely used. So first of all, the definition, it says for each subtree, the left node should be less than the root node, which should again be less than the right node. And if you want me to draw an example, it would be very easy. 30, 50, 10, 20, 5, 40, 60. I think we have taken the example in our introduction as well. And if not, I would request please see that video. If I come to its usages, where applications, where it is used. Searching, sorting, heap sort. I have covered already. Searching in a binary search tree, I am going to cover today. So let's see how searching is efficiently performed in a binary search tree, and I am going to extend this example only. So let's see, we have more data. 100. This should be at the right, so 55. This should be 35. Here we can have 1. Here we need to have 15. Okay. Assume you have to search 35 in this one. Our target is to find 35. So what we will do is, we will start from the root node. Our target is 35. It is smaller or larger? It is larger. That means we are sure that left node we can ignore because that's the property. So we will ignore this entire subtree. We don't need it. And we move towards right. Now at this point, we again search 35. It is smaller or larger than our new root? It is smaller. So at this point, we can entirely ignore this right tree and move towards the next part. Now at this point, again search 35. It is smaller. So there is no right child of 40, but in case if it was, then just ignore that entirely and move to the left part. And here we find our answer. So you can see that in this structure, which is having 12 nodes, and we are able to find our answer in just 3 steps. In just 3 steps. We first went from 30 to 50, first step, then 50 to 40, second step, and then 45 to 35. In only 3 steps, we were able to find our answer. See how efficient this was. If you have to search this in an array, then you have to traverse the array from the beginning. That is why binary search tree is widely used in searching algorithms. It is very, very efficient. And there is one more property of a binary search tree. And it is that property is, and it's an application also, it keeps the data in ascending sorted order. Some of you might say how it is possible. So let me remove all these red marks. As you can see, I mentioned that it keeps the data in ascending order, sorted order. But some of you might say, we cannot see the sorted because it is 30 and then 10 and 50. What kind of sorting is this? Well, there is something called in order traversal of a binary tree. There are 2 more, pre-order and post-order. We are going to cover all these 3 in separate video. But when you do an in-order traversal, in that, what you do, you first go to the left node, then you print the node, and then you go to the right node. These three steps are performed at each level. So when you are at 30, you move to the left node. I move to 10. Again, I will move to the again I will apply all the three steps at each level. So for at 30, first step is done. I move to 10. Again go to left node. I move to 5. Again go to left node. I move to 1. There is no left node of 1. So I will print the 1. Then move to right node. There is no right node of 1. I move it its parent because it is recursively happening. For 5, we have just completed the first step. Move to the left node, which was 1. So at the second step, I will print 5. There is no right node. I will move up. For 10, left node, first step was done of moving to left node. Second step was printing. I move to 10. Then I move to right node of 10, which is 20. Now for 20, again, the first step will be done. Move to the left node, which is 15. No left child, print 15. No right child, move back, print 20. No right child, move up. Right child done, 10. For 10, we have done all the three steps, move up. For 30, only first step was done, print 30. Move to the right child. For 50, again perform three steps. First step, move left. Again first step, move left. 35. And in this order, if you keep on going, you are going to get the data in sorted order. If you are not able to follow, don't worry. You can rewind back, see at how at each step I am performing each operation. Else, I am going to cover all these three in order, pre-order, post-order traversals in depth with example, with code in another video. I think we have covered the applications also. One thing that was left for the type of binary search trees is something called self-balancing trees. There are two types, AVL trees and red-black trees. Now, why self-balancing trees are needed? So if you remember, there was something called as skewed tree, right? We heard about this. This is a skewed tree. There's only one node at each level. As I mentioned, there is no purpose of having such a tree. It is not solving our purpose. So rather, what we should have is, we should convert this into a complete binary tree. See above what is the definition of complete binary tree if you do not remember. Pause here, go back, see it, and then come back. So what we will do is, at each level, we will remove a node and we will convert it into a complete binary tree. It is still not. It is still not. Now this is a complete binary tree. Now I have done this in an arbitrary manner. In reality, AVL tree and red-black trees are advanced algorithms that define how you should balance a skewed tree so that the property is remained intact. The relationship that you have defined for a tree, that remain intact. Okay, so we will be having entirely different video on these two subjects. As of now, just understand that self-balancing trees are there to make a skewed tree into a complete binary tree. So self-balancing tree, what it does, they convert a skewed tree into a complete binary tree so that we can effectively use it for the purpose that we have binary trees. That's all for this video. If you have any doubts, please do let me in the comments below. And there are many topics that I have just touched in this video, and for those we are going to have a entirely different, in detail, in depth with code video. So see you again. Till then, have a great day. Bye.